Most engineers treat rate limiting as a binary problem. A request is either allowed or blocked. The counter is either under the limit or over it. But here is a twist. That framing is exactly what gets teams into trouble. When Cloudflare built rate limiting for millions of domains, handling attacks at 400 requests per second, they ran their algorithm against 400 million real requests and published the result. 0.003% is wrong. Some legitimate users were blocked and some bad traffic let through. And guess what happened next? They shipped it anyway, because that 0.003% is not a bug. It's the price of an algorithm that scales to billions of requests without collapsing under its own weight. And here is the kicker. They chose that failure mode. They knew exactly how their system would fail and decided that trade-off was worth it. The question isn't whether your rate limiter is perfect or not. It's whether you made that same conscious choice or whether your implementation just fails in ways you've never measured. Let's start with the concrete problem. You have an API, it's receiving traffic, normal traffic, a few hundred requests per minute. One day, something changes. Maybe a client has a bug in the retry logic. Maybe a competitor is scrapping your data. Maybe someone is running a credential stuffing attack against your login endpoint. Sounds familiar? Without rate limiting, every single one of those requests hits your backend. Your database starts queuing queries it can't keep up with. Your connection pool exhausts. Response times climb from 20 milliseconds to 20 seconds. And then, one by one, legitimate users start getting errors. Not the attacker, your real users. But here is what most people miss. The cost isn't just downtime. It's the AWS bill that doubles because one poorly behaved client decided to retry every failed request 3 times in parallel. It's the database that needs emergency scaling at 2 a.m. because nobody capped how many times a single user can call your most expensive endpoint. Rate limiting isn't just about attackers. It's about protecting your system from anyone who sends more traffic than you designed for, including your own clients. And now, here is the kicker. Most teams know they need rate limiting. They implement something, they test it, it works. And then they find out in production that what they implemented isn't actually what they needed. Let's look at why, starting with the algorithm almost everyone reaches for first. The fixed window algorithm. Fixed window is the most natural mental model. Divide time into discrete pockets, 1 per minute, 1 per hour, whatever your window is. Each request increments a counter. When the counter hits your limit, you start returning 4 to 9s. When the window resets, the counter resets. Simple, easy to reason about, and easy to implement. The implementation is clean. You compute the current window ID, namespace every key to a window, so when the window rotates, the old key naturally expires and a new counter starts with no manual cleanup. Then increment the counter. And if this is the first time to increment this key, or if for any reason the key doesn't have an expiry, you set its expiry to the end of the current window. Then compute the needed values for your HTTP rate limiting headers, and that's it. But wait, there is a problem, and it's not subtle. Here is the boundary parsed. Your limit is 100 requests per minute. An attacker or a buggy client sends 100 requests at 11:59:59.8. All 100 are allowed. When the one counter hits exactly 100, then 0.4 seconds later at 12:00.2, they send 100 more. When the 2 just started and its counter is exactly at 0, all 100 are allowed again. That's 200 requests in under half a second against a 100 per minute limit, while both windows technically respected. And this is not theory. Here I created a test in our production starter kit to prove the boundary parsed attack exists. Our limit is 100 requests per minute. We start the test by sleeping until just before the exact minute ends with 0.2 seconds. Fire 100 requests, sleep 400 milliseconds, and then fire another 100 requests. Then asserting that we sent 200 successful requests in less than half a second. This is not a bug in the code. The code is correct. The implementation exactly matches the algorithm specification. The problem is that the algorithm has a structural flaw and it's predictable. Anyone who knows your window size knows exactly when to fire the requests. For a login endpoint, that's a brute force amplifier. For a public API, that's a cost exploit. for a scrapping target, that's a free double throughput. So what do you do instead? You need an algorithm that doesn't have hard boundaries. You need a sliding window. The ideal solution would evaluate every request against the exact last 60 seconds of traffic, not a 60-second window that resets at 12:00, a window that ends right now, at the precious moment the request arrived. That's called a sliding window log, and it works exactly that way. Every request timestamp is stored, and when a new request arrives, you count how many timestamps fall within the last 60 seconds. But here's the twist. Storing every timestamp doesn't scale. If a user makes 1,000 requests per minute, that's 1,000 timestamps per user per minute. Scale to 100,000 users and you're storing 100 million timestamps. Your Redis memory explodes. Your cleanup jobs can't keep up, and the operational cost is enormous. This is the trade-off I was talking about in the beginning. Perfect accuracy at unacceptable cost. The sliding window counter is the practical answer. Instead of storing every timestamp, you store just two numbers, the current window counter and the previous window counter. Then, when a new request arrives, you estimate the rate using a weighted approximation. Let's say you're 15 seconds into the current minute, which means 75 of the previous minute is still within your 60-second sliding window. So you count 75% of the previous Windows requests, plus all the current Windows requests. In this example, one more request in the next second and the rate limiter will start to get very angry. Now, here is the kicker. This is exactly the algorithm Cloudflare uses at scale. Remember that 0.003% error rate from the beginning? That's the measured cost of this approximation. The formula assumes the traffic was evenly distributed throughout the previous window, which isn't always true. If all 42 previous requests happened in the last 5 seconds of the previous window, the formula underestimates the real rate. Some traffic leaks through, but across 400 million real requests, Cloudflare measured that leak at 0.003%. That's the conscious trade-off. A tiny measurable approximation error in exchange for big O of 1 memory and big O of 1 computation. You're not ready for this, but it also solves the boundary parsed completely. Because the window slices continuously, there is no hard reset to exploit. When the new window starts, the previous 100 requests are still heavily weighted in the formula. The attacker who sent 100 requests at 59.8 seconds can send another 100 at 60.2. The formula knows those 100 requests just happened. The implementation is straightforward. You compute the current and the previous keys based on the window ID, get post counters from Redis, calculate the approximated rate, and if it's greater than or equal the limit, reject the request. The implementation detail that matters here, notice we get post counters first, calculate the rate, and only increment if the request is allowed. This is not the order most implementations use. Most do increment first, check, then decrement if over limit. But increment then decrement has a race condition under concurrent load. Two requests arrive simultaneously, post increment, post read an inflated counter, post get allowed, or post get denied incorrectly. Get check increment wrapped in a single Lua script eliminates that race condition entirely. By the way, Lua scripts runs atomically because Redis is a single threaded and no other commands can execute on Redis while the script is running, so it's atomic. If you wanna me dive deeply on Redis and its Lua scripts in a future video, please let me know in the comments. Now let's get back to rate limiting. Sliding window is the right default for most APIs, but there is a class of use cases where it's the wrong tool, and if you use it there, you'll spend time debugging why your legitimate users keep getting throttled. Here's a scenario. Your API has a mobile app client. The app is in the background for 10 minutes. The user opens it. In the first 2 seconds, the app fires 15 requests, syncing state, refreshing tokens, loading the dashboard, or whatever it does. That parse is legitimate. It's not an attack, it's normal app behavior after a period of inactivity. A sliding window with a tight limit will throttle this user every time they open the app. That's a bad user experience from correct rate limiting. Token Bucket uses a different mental model. Instead of recent history, it models capacity. Imagine a bucket that fills with tokens at a constant rate, say 2 tokens per second. Each request consumes 1 token. If the bucket is empty, the request is rejected. If the user is idle, tokens accumulate up to a maximum capacity, say 20 tokens. When that user opens the app after 10 minutes, their bucket is full. They can parse 20 requests immediately, then settle into the 2 per second millisecond sustained rate. The implementation tracks two values per user in a Redis hash, the current token count and the last refill timestamp. On every request, the script calculates how many complete refill intervals have elapsed since the last refill, adds that many tokens up to the bucket capacity, then deducts one if the request is allowed. But wait, there is a subtle bug hiding in the timestamp update that breaks refill accuracy. If you set last refill to now every time you add tokens, you reset any fractional interval progress already accumulated. Imagine your refill interval is 1 second and you last refilled 700 milliseconds ago. You already earned 70% of the next token. If you reset last refill to now, that 700 milliseconds disappears. The next token will not arrive for another full second instead of 300 milliseconds. Over time, this makes your token bucket refill slower than configured. The fix is to advance last refill by exactly the number of complete intervals that elapsed, preserving the fractional progress into the current interval. Now, here is the decision. When do you use each one of these algorithms in production? The mental model that makes this clear. Fixed window asks about discrete accounting periods, so it's only usable for internal simple use cases. Sliding window asks what have you done recently. Token bucket asks how much capacity have you earned. For a login endpoint, recent history is what matters. You don't want someone to accumulate parsed capacity and then use it for a credential stuffing run. For a developer API, earned capacity is what matters. A client that has been idle for 5 minutes has legitimately earned the right to parse it. You have it chosen your algorithm. Now, where do you put it? This decision gets less attention than the algorithm choice, but it determines what information your rate limiter actually has access to. And without the right information, even the right algorithm enforces the wrong thing. Here is the rule. It's one sentence. Your API gateway sees the HTTP request, headers, URL, IP address, API key, JWT claims, things like this. If your rate limiting rule can be expressed entirely with those 100 requests per minute per API key, for example, the gateway has everything it needs. Put it there. The request gets rejected before it touches your application servers. Clean, efficient, and no application code involved. But here is the twist. The moment your rule needs something the HTTP request doesn't contain, for example, the user subscription tier from your database, their account status, a business rule like premium users get 10x the limit, your gateway can't access that without an additional call. And now you have added latency and a dependency to every request just for the rate limit check. In that case, middleware inside your application is the right layer. You already have the user context there. Use it. One thing to flag on the dedicated service option. It gives you centralized control, but every request now pays an additional network round trip, even at 5 milliseconds. That adds up at scale. We'll cover the distributed rate limiting problem in the next video. There is a lot more to say about it than fits here. For most single service APIs, gateway or middleware is the right answer. Let's wire this into a real application. I have 3 endpoints: sign up, sign in, and a get user endpoint that requires authentication. Each one needs different rate limiting behavior, which is exactly the kind of real world scenario these algorithms were built for. Sign up and sign in use sliding window by IP. We want strict fairness here and no parse tolerance. Someone accumulating tokens and then firing a parse of login attempts is exactly the attack pattern we don't want to allow. The authenticated get user endpoint uses token bucket by user ID. Authenticated users have legitimate parsed patterns, and we can enforce fairness at the user level rather than the IP level. The rate limiting interceptor holds the logic to enforce rate limiting. It first resolves the configuration of the annotation. It first gets the annotation, and if there is no annotation on the endpoint, either on the endpoint level or the class level, it defaults to token bucket. Then it checks the configuration key. It returns the configuration matching the key from the application properties file. If the configuration key is not provided, then it returns the fixed data from the annotation itself. After resolving the configuration, it resolves the rate limiter based on the algorithm field in the configuration. Then it resolves the client ID. And if the user is authenticated, the client ID is based on user ID. We get it from the JWT token. And if the user is not authenticated, then we use the IP address. And after all of that, the interceptor now checks the limit with a configured rate limiter. And we have different options here. We have sliding window counter, fixed window with Redis, token buckets, and each one of these algorithms connects with Redis and running a Lua script on it. The Lua script here is a little bit advanced than the one showed in the video because it's more production level, handling more edge cases. Then it calculates the rate limit result, which is then returned to the interceptor to be set in the rate limiting headers. And if this request is not allowed, then we throw a rate limiting exceeded exception. Let's see this into action. I'll first call the sign up endpoint here, then refresh Redis. And here we can see our rate limiting key, which is rate limit colon IP colon the IP address itself, then the window ID. And we have a value of 1. Then I'll call the sign in point, refresh Redis again. Now the value is 2. Then let's wait a little bit to make sure the window has elapsed and call the sign in again. Now you can see another key has been generated with the key pointing to the next window. And if we keep calling sign in, we will get eventually the rate limiting exceeded exception. And let's check the headers. And here we can see the rate limiting headers as returned in the response header. But if I call the get user by ID endpoint and refresh Redis, we will get a different key here. First, it doesn't have a window ID and it's related to the user and it has the user ID in it. It also is a hash. It's not a string. It has 2 values, the tokens and the last refresh. If I called it again, the token has increased and the last refresh has been updated. When a request is rejected, it returns all the 4 standard headers. X rate limit tells the client what the limit is. X rate limit remaining tells them how many they have left. On a 4 to 9, this is a 0. X rate limit reset tells them when the window resets as an epoch timestamp, and retry after tells them how many seconds to wait. A well-behaved client that reads these headers can back off intelligently instead of hammering your endpoint with retries that all return 4 to 9. You now have 3 things: a working implementation of sliding window counter and token bucket in Kotlin and Redis, a decision framework for which algorithm fits which use case, and more importantly, an understanding of how each one fails, not from a textbook from the code. But here is what we haven't solved yet. Everything we built today works correctly on a single Redis instance. Deploy this to 3 application servers and something breaks. Not the algorithm, not the Lua script, but the distributed counter. 3 servers, each making correct decisions based on a shared counter, still allow more traffic than your limit when the counter itself becomes inconsistent across nodes. That's the distributed rate limiting problem. It has specific failure modes, clock skew, hotkeys, split brain, and specific solutions. That's what the next video covers. If something wasn't clear or you would do something differently, leave it in the comments. See you in the next one.